Boa tarde para todo mundo. Bem-vindos ao último seminário desse semestre. Os seminários do próximo semestre vão iniciar muito cedo, então. Hoje, incidentalmente, só um anúncio logístico. Vou mandar um doodle na próxima semana para o dia, o tempo e a hora que você queira, que você preferiria fazer o seminário no próximo semestre. Pode mudar, porque o tempo das aulas pode mudar também. Vou mandar um doodle. Hoje temos a honra e o prazer de ter o Eduardo Peinado, da Universidade Nacional Autônoma do México. Eduardo fez o doutorado lá e depois fez pós-doutorado na CSIC em Valência, Instituto de Física Corpuscular, e no Laboratório de Frascati, na Itália. Agora é professor na Universidade Nacional Autônoma do México. Ele vai falar da conexão entre física de neutrinos, dark matter e simetrias extramodelo padrão. Como sempre, por favor, todos exceto Eduardo, desliga o vídeo e áudio. Depois vamos ter perguntas. Se alguém tem uma pergunta curta e urgente, pode mandar mensagem no chat. Para estudantes, pode pôr o seu nome na lista de presença no chat. Eduardo, você pode iniciar.
So thank you very much. Muchas gracias. Muito obrigado. Thank you very much also for the kind invitation, Giorgio, and for the nice presentation. So today I will talk about neutrino physics, dark matter, and U1 symmetries. U1 in general, I mean, I will talk about a bit on B minus L, on U1 prime, that in general can be B minus something, or only leptons, and the Peccei-Quinn at the very end of my talk. So my point is to connect neutrino physics with dark matter using this kind of symmetries. It can be global or gauge, but I will go through this during the talk. Okay. So we know that the standard model works pretty well, better than we expected some years ago. So we have the fermions, the quarks and leptons. We know that there are 3 families, at least, as far as we know. And we have the gauge bosons and the Higgs mechanisms, okay? So we know that the standard model consists on a product of gauge groups, SU3 of color, SU2 chiral, I mean left, and U1 hypercharge that is broken by the Higgs mechanisms into the U1 of electric charge, okay? So, but we know also that the standard model is not complete because there are several issues that does not have an explanation within the standard model, like for instance, the baryon asymmetry in the universe. By the way, did you see my pointer? The mouse, Giorgio?
Yes, okay. Yes, we do.
Perfect. So we also know that we have dark matter, I mean, a kind of matter that is not the baryonic one that we know. And the density in the universe is huge in comparison with the normal matter. It is like 85% of the matter in the universe is what we call dark matter. And somehow neutrinos that are massive particles, when the standard model was built, were considered massless. Okay, so neutrinos, we know that they oscillate and they have masses. So we have to include neutrino masses in the standard model. Okay, so the issue is, can we understand at least these issues beyond the standard model in connections with neutrinos? Well, there are several answers. For instance, to connect baryogenesis with neutrinos, we can use leptogenesis. I mean, we generate an asymmetry in leptons, and then by Sphaleron processes, it can convert into baryons. Or there are some kind of similar mechanisms to baryons that there's a mismatch, etc. But I will not talk about this. I will concentrate on dark matter. Of course, there are issues, or there are models that can try to connect the three of them. Actually, some extensions of what I will explain today, you can also have baryogenesis, but I will concentrate on this connection. Okay. There are some possibilities, WIMPs. It can also be a sterile neutrino of the order of kiloelectron volts, even though that now is kind of difficult to produce them and to be consistent with other observations. It can be that a pseudoscalar that is connected to the breaking of lepton number. If neutrinos are Majorana, it can also be a dark matter candidate. And you can have some WIMPs that gives you a kind of small neutrino masses through a loop, and inside the loop you have what is the dark sector. Okay, there is a famous model for that called scotogenic, and I will come back to this particular case in a few minutes. And there are other options. Okay, so we know neutrino oscillate. I mean, they change flavor when from the source when you produce neutrinos, for instance, in the sun, in a reactor, or in the top of the atmosphere when a cosmic ray hits the atmosphere, it produces a bunch of particles, and those particles decays pions, etc., into neutrinos. So we also have geoneutrinos, and we also produce neutrinos, etc. So neutrinos are everywhere, and the point is that when they travel, there is a probability, non-zero probability, that they can change the flavor. I mean, for instance, in the sun, we produce, the sun produces electron neutrinos, and what we see in the Earth is that some of those neutrinos are converting. I mean, in the path, they convert to muons and tau neutrinos. Okay, so that is basically the proof that neutrinos are no massless particles. Okay, so since they have masses, we have to include massive neutrinos in the standard model. Okay, so what is the status of neutrinos? What do we know about neutrinos, or what we don't know about neutrinos? I mean, there are two possibilities. We have three active neutrinos, light active neutrinos. I mean, with masses below half of the mass of the Z boson. And we can have a normal hierarchy. That means you have a very massive, I mean, a heavier neutrino and two lighter states, or you can have two almost degenerate neutrinos and the other one that is light. So that is what we call normal hierarchy and inverted hierarchy. Okay, so we don't know this. We don't know, even though we have a hint about if neutrinos violate CP in the oscillation. There are two possible sources of CP violation in neutrinos. If neutrinos are Majorana, one is the one in the oscillations, and the other one is what we call Majorana phases, that they are not observable in the oscillations, but there are some processes like neutrino double beta decay. Basically, you can have neutrino beta decay that produce anti-neutrinos of electrons. You can also have double beta decay with two anti-neutrinos of the electrons in the final states. But if neutrinos are Majorana particles, you can also have neutrino double beta decay, and the Majorana phases affect this process. Okay. We know that neutrinos are very light. I mean, way lighter than the electron, which is the charged fermion, the lightest charged fermion we have in the standard model. So the last Catherine data tell us that the effective electron-neutrino mass is below 1 electron volt, okay? And if the cosmological model is what it is the final answer, that means that the cosmological observations tell us that neutrinos are even lighter than this, and the sum of the 3 light neutrinos, active neutrinos, is less than 0.12 electron volts, so are really, really light, okay? Since they oscillate in the 2 flavor case, you have one mixing angle, one difference, square mass difference, and in the 3 neutrino oscillation case, which is what we have in nature, you have 3 mixing angles, like in the case of the quarks in the CKM. We also have 2 mass differences, because the third one is a combination of the 2 difference between, for instance, between the 2 and the first neutrino, and the 3 neutrino 3 and neutrino 1, or neutrino 3 and neutrino 2. Okay, so we have from the oscillation parameters only 2 square mass differences. So we don't know what is the mass of one of the single neutrinos. We also have some bounds. Okay, it should be less than 0.12. Is we believe in the standard cosmological model, or if we say, okay, let's wait a bit, it should be at least the effective mass of the neutrino, of the electron, less than 1.1 electron. Okay, so we have 2 large mixing angles, like for instance, the solar mixing angle, that is the θ12, is big, if you see here. Where is this, the small one? Okay, the θ13 is the one that is very small, is 10 to minus 2, while the other 2 are like 0.3 and 0.5, more or less. Okay, so this is very different what we have in quarks, where we have only one big mixing angle, which is lambda Cavibo, and is 0.2 around, which is small, but it's non-zero at least. And in the case of neutrinos, if we compare, for instance, this is the CKM from the PDG. If we compare the biggest mixing entry, it is of the same order of the smallest in the neutrino sector. Some years ago, before 2011, it was consistent, all this, this is coming from global fit, from all the oscillation experiments. It was consistent with 0. Basically, it was less, it should be less than 0.02 or something like that. Something like that. It was only an upper bound. And with that, basically, it was nice because you can parameterize these numbers here like this, and it was called tri-bimaximal because you have 3 of them mixed in the same way, and 2 of them maximally mixed. Okay, this was called tri-bimaximal. If you see this, can tell you more or less that maybe there was at that time a symmetry behind this. So it was very popular, and many people did a lot of work in flavor symmetries for neutrinos, including myself. But after Diabate, we know that neutrinos, this 0 here is non-zero, and by a lot. This is around 0.15. So of course you can use flavor symmetries and break them and so on and so forth, but it's less appealing than before. Okay. So we have beta decay. For instance, Catherine is an experiment of beta decay, and they try to measure or try to infer what is the size of the light neutrino mass. We have also, in the case of Majorana, there are several experiments running on this, neutrino last double beta decay, because I will explain later this, but if you observe this process, that means the neutrinos are Majorana. So we don't know if neutrinos are Majorana, That means that they are their own antiparticle, or are Dirac like the rest of the fermions in the standard model. And from cosmology, we have a parameter that is the sum of the masses. So you can combine them and play a bit, and you can plot the lightest neutrino mass versus the sum of the masses, and you see for normal hierarchy and inverted hierarchy. So if cosmology continue going down, maybe you will have some restrictions for this, okay? So this is for normal, and this is for inverted hierarchy, okay? You can also combine the cosmology with neutrinos double beta decay, and those are the allowed regions with the 3 sigma in the oscillations. For instance, this is for the invert hierarchy. This is not up to date. I think is the bound is around here. But in any case, if neutrinos are in the most favorable now, that is the normal hierarchy, it is possible also that this process is 0 or very, very small, because there are some cancellations within the Majorana phases. So if you don't observe this process, you cannot say that, or you cannot claim that neutrinos are Dirac. But the only thing is that if you observe this process, that can tell you that neutrinos are Majorana particles. Okay, the idea is to combine this observable to exclude at least part of the region of parameters. Okay, so this is basically the way particles couples to the Higgs, and this is the mass of the particles are basically the coupling with the Higgs and the back of the Higgs. So this is the latest results coming from CMS. Atlas, they also have a kind of similar plot. The thing here is that if you see the muon, which is the second heavier lepton, I mean, now we also have measurements for the Higgs coupling with the muons, which is, to me, is kind of outstanding. And the outstanding thing is that it basically fits perfect with the standard model. Okay, so up to now, the standard model is like even stronger than before. So this is basically all the masses we have for fermions. I mean, we have the top mass, which is the big one here, the big guy with a coupling of order 1. And we have the electron, for instance, that the coupling is 10 to minus 5, 10 to minus 6. And I mean, we have no data for Higgs with electron, and we will not have it unless we have a precision machine for Higgs. I mean, and that I don't think will happen, at least in the near future. So if we consider neutrinos, as I told you, muon, for instance, that is in here, is the mass of the muon is, 100 MeV. So this is 0.5 MeV, so it's somewhere in here. And if we consider neutrinos that are of the order of 1 electron volt or even less, well, these continue and are very far, right? So how can we explain neutrino masses? Of course, this is, I mean, for instance, the fermions are coming from the Yukawa couplings that are in here. This is for sharp leptons, quarks down and quarks up. So you can include the right-handed neutrino in the standard model, and that's it. Okay, but the problem is to explain why they have Yukawa couplings of order 10 to minus 13, 10 to minus 12, while the rest of the fermions are above 10 to minus 5. Okay, so there are some ways, like the seesaw mechanisms. There are several ways to understand. Basically, it consists on having a heavy scale that tells you why these light neutrinos are so small. They are surprised by this heavy scale. There are also some low scale seesaw that I will show one at least. And of course, as I mentioned, they can be Dirac, and then you have to explain why this Yukawa coupling is so small. Okay, so the question is Dirac or Majorana particles. If they are Dirac, then you will not see anything in the experiments of neutrinos double beta decay. If they are Majorana, you have chances to observe this process. And I hope they will. Otherwise, we will be like with this question for many years from now. So the simplest way to have a Majorana mass for neutrinos without giving details of the UV completion is the dimension 5 Weinberg operator. Basically, Weinberg, what he did is to classify all the operators that break either lepton number, baryon number, or both. So the smallest operator was dimension 5, and that violates lepton number. Since it is dimension 5, you have 1 over the scale in here. So if this scale is big enough, then you explain the suppression of neutrino masses. And as I mentioned, this violates lepton number into units. And there is a theorem by Schechter and Valle, which I told Giorgio that he's Brazilian. It tells us that if you observe this process, the neutrinoless double beta decay, that means that the neutrinos are Majorana particles, okay? So, CISO, how can we UV complete this Weinberg operator? Okay, so in the standard model, the L stands for the lepton doublet that contains electron and neutrinos. The Higgs is a doublet, and we know that doublets times doublets in SU2 is singlet and triplet. So either you contract to singlet or either you contract to triplet. In the case of neutrinos, we need the triplet because this part, I mean the LL violates weak isospin, so you need the triplet. Okay, so the easiest thing is to include the right-handed neutrino. Then this is the Dirac of like the rest of the fermions. You can also have the doublet of lepton, doublet lepton, and the triplet of one scalar that is triplet. And if this take a BEV, then you explain neutrino masses. And instead of having a fermion singlet, you can also have a fermion triplet. Okay, so the diagrams, or diagrammatically, how we do this is basically this. If you close this or integrate this field here, then you have the dimension 5 Weinberg operator. If you integrate this heavy field, you also have the dimension 5 Weinberg operator, and also for this guy. So you have 3 options in the case you have this kind of particles. And basically, if you have, for instance, this matrix is 3 plus n, you can have n right-handed neutrinos or n triplets. The minimum is 2, because with 2 you generate a rank 2 matrix for the light neutrino masses with the CISO. So the minimum is 2, but the maximum can be whatever you want. Okay, so this part is coming from type 2. This part is coming from either type 1 or type 3. I mean, singlet fermion or triplet fermion. And this is coming from the Dirac term, normally from the Higgs. Okay, so there are other more exotic CISOs, like I mentioned before. This is the case of one low scale CISO. You have double suppression. This is the inverse CISO. Basically, you include another state that is like the right-handed neutrino, but under lepton number, global lepton number, transform differently. Okay, so basically what you need is to include a small term here that violates lepton number, and then the neutrino masses are coming like this. You have double suppression for the heavy mass in here, and the suppression coming from this mu parameter. So in that way, you can bring down this scale. So this is what we call an example of low energy CISO. Okay, and if the mu parameter is 0, then you recover Dirac neutrinos. Okay, you can also generate neutrino masses through radiative corrections. I mean, if you basically forbid the 3-level neutrino masses, then you can generate the dimension 5 Weinberg operator at 1 loop or more loops. And you have extra suppression coming from the loop factors. Okay. And as I mentioned at the beginning, the scotogenic basically is like this kind of models, but with the dark matter inside the loop. So this N, which is kind of a right fermion, is a sterile singlet neutrino. And this eta is like the Higgs, but is part of the dark sector. Those particles are stable by means of Z2 symmetry. And in this kind of models, you have the Higgs portal. I mean, the dark matter, when, for instance, this term here, that is one of the quartic in the potential, when this guy pick up a wave, you have the Higgs and two dark matter particles, scalars. Okay, so you have the Higgs portal, and you can also have direct detection. Okay, so this is what we know. So what about dark matter? We know that dark matter is stable at least at cosmological times, so it should have a lifetime bigger than this, the age of the universe, and or be basically long-lived, what we call very long-lived, or really stable. And if that particle is stable, you need a symmetry that protects this dark matter from decaying. Okay, so in my opinion, it is easier to consider dark matter that is stable because you have a symmetry, and that's it, like for all the stable particles in the standard model. So one symmetry could be U1. U1, basically you have, that is a circle. And you have also from U1, you have some residual symmetries like Z2, which is the I mean, this is the, here is the 1 and here is the -1. And this is the complex plane, okay? You can have also Z3, all of them is radius 1. You can have Zn with several points in here, okay, related. So when you have a U1 symmetry, you can easily have some residual symmetries. One, this U1 is broken. That is the point of this slide, okay? So, but what about Dirac neutrinos? I mentioned that if you have Dirac neutrinos, you have to, either you put this coupling to be 10 to -12 by hand, or you have something that explains why this effective operator is small, okay? For instance, this is a dimension 5 operator with one, the doublet, lepton doublet in here, a right-handed neutrino in here, so it is a singlet, so you need the Higgs, and you have a scalar that gives you the dimension 5 operator, okay? This is a 2-loop, because a 2-loop you have double suppression coming from the loops. And in this model, it was just only to exemplify that you can have suppression of this effective Yukawa coupling by means of this kind of models. By doing that, you need to explain why this particle in here, that is the right-handed neutrino, that is singlet of the standard model, does not take a mass, because if this is singlet of the standard model, there is nothing to forbid the mass term, like nu c bar nu, which is a Majorana term. So you need a symmetry, and for that you can use either lepton number or this Z3 symmetry, for instance, which is the smallest. Z2 doesn't work, because Z2, if this is -1, this is allowed because it's a bilinear, okay? If you want to have 2 loops instead of 1, you need a Z3 symmetry. Z2 doesn't work. Z2 you can have, like in the scotogenic that I mentioned before, 1 loop. So with this Z3, at the end of the day, what happens is that all the particles inside the loops are stable. And in order to suppress or to kill the 3-level term between the left-handed neutrino, the Higgs, and the right-handed neutrino, you need another symmetry, okay? This was a model. We explained basically dark matter, why the Yukawa coupling is small, and etc. It was just to exemplify, okay? The question here is, do we really need these 3 symmetries to do this? I mean, to have naturally small Yukawa coupling for Dirac neutrinos? So the answer is no. if you have U1 B minus L, that means that all the baryons are +1 and all the leptons are -1. And this symmetry is already present in the standard model. I mean, baryon and lepton number are basically accidental symmetries of the Lagrangian if you don't include lepton masses, neutrino masses, sorry. And if Majorana, if neutrinos are Majorana, then you have to break the lepton part at least, okay? So, but if you have this symmetry and you consider it as a symmetry that can be gauge or global, and you break it by means of some scalar fields, the way it breaks will tell you if neutrinos are Dirac or Majorana particles. For instance, if the set M here is odd, like 2M plus 1, then neutrinos are Dirac particles because you will never get the term like neutrino, a neutrino, and a mass term here, okay? So in that case, if this is, for instance, set 3 or set 5 or so on, neutrinos are Dirac particles. If, on the other hand, neutrinos, I mean, this breaking is to a set 2n, which is even, set M is, I mean, M is even, then neutrinos can be either Dirac or Majorana, depending on how they transform, okay? If this is set to n, if neutrinos transform as n, then you form a Majorana mass for neutrinos. Okay, you can have neutrino, and a mass, because they will transform as omega to the 2n, which is 1, so it's an invariant. But if they transform differently, for instance, if you have set 6 and they transform as omega squared, then they should be Majorana, Dirac particles, okay? We need to forbid this kind of terms. So if you have 3 right-handed neutrinos, you have 2 solutions that are anomaly free. If neutrinos transform like the rest of the leptons, like -1, then you can form this term here, okay? Because this is +1, this is -1, and this is an invariant. But the other solution is to have -4, and 5. If this is the case, there is no way to have this term in the Lagrangian. So you forbid the 3-level Yukawa couple. But you can generate this term by means of scalar fields. So you can generate a dimension 5, 6, or whatever you want, okay? So if we choose this, then we solve the first, no 3-level term, okay? So as I mentioned before, if this is one of the examples, but if this M is even, neutrinos can be either Majorana or Dirac, okay? So for this particular case, what we did is to break the U1B minus L. The neutrinos are -4, and 5, and you need some fermions to generate this loop. And you have to be sure that those fermions does not spoil the anomaly-free solution, which is the case because they are vector-like. In this case, what we have is that you can break set into an even number here, and this is because if you have an even symmetry here, you can have that those particles inside the loop are stable. So this is one of the solutions one of the recipes we found to have dark matter. So to solve this part of having an extra symmetry to have stable particles inside the loop, okay? So no 3-level is coming from the solution of having, instead of -1, the right-handed, to have -4, and 5. So we have solved these 2. This is by the solution of anomaly free. This is coming from the way you break the symmetry, the U1B minus L. You need a set 2n, which is an even symmetry. That means that if this is even, you can have Dirac neutrinos or Majorana neutrinos. Okay, so we construct a model for Dirac neutrinos, and basically we moved to set 6 because in set 4, to my colleagues, they didn't like the charge they found. They were very high, so we stick on set 6 just to give an example. And automatically we found how these particles inside the loop are stable. Okay, basically the recipe is more general. You can generalize to n loops. And the point is this: if the standard model leptons are even powers of this residual symmetry, particles inside the loop, you have fermions and scalars. And if they transform odd under this residual symmetry, they are automatically stable. On the contrary, if the standard model leptons are odd under this symmetry, you can have either scalar or fermion, depending on how the way they transform. If the dark matter is a scalar, and it basically, if this dark matter transform as odd, it is automatically stable because you will need at least an even power of fermions, number of fermions in the final state. And if they transform out, at the end of the day, the symmetry in the final state is even, so this scalar particle is stable. If the fermion is the dark matter 1, the lightest inside the loop, and if this fermion transforms as even, it will be automatically stable because you will need an odd number of leptons in the final state, and that means that they will transform as odd. Okay, so with this, you have stable dark matter inside the loop. Okay, so you can have, we also have an example for Majorana in this. I don't know if you see it because this is, okay. For Majorana neutrinos, you can also have Majorana because this is even, the symmetry. So you can see in this paper. Okay. Okay, so I will move to the Peccei-Quinn case. Basically, the Peccei-Quinn is the most popular solution for the strong CP problem. And there are two kind of models. One is the KSVZ model, which basically consists on the standard model is not charged under the Peccei-Quinn. And then you have exotic quarks, heavy exotic quarks that transform under the Peccei-Quinn. Or you have the DFSZ model that you have the standard model that is charged under the Peccei-Quinn. So if we take this, the second one, basically you need two Higgses, one for the up and one for the down. And there are two possible solutions. One is when you have a trilinear coupling, and basically HU, HD, and the Peccei-Quinn field, or the quartic coupling that you have HU, HD, and 2 times the Peccei-Quinn, okay? And if you take this solution, the trilinear coupling, so K is dimensionful, it has dimension 1 under the mass, and in basically all the fields transform equally under the Peccei-Quinn, okay? This should be the left fermions, okay? So basically you can have Q bar U and HU and so on and so forth. Basically you can give 2 charge under the Peccei-Quinn. So this is 2, 2, and this is 4 to have this term. And if it happens, what we found is that neutrinos cannot be Majorana particles. Basically, there is no way to generate lepton number violation. Delta L equal to operator at dimension 5 or a dimension higher than 5. So basically with this is 1, this is 1. This is 1, this is, L is 1, and H up and H down are 2. So you can have either HU coupled to the leptons, or you can also have HT. With one the tilde, the other one the normal. because the hypercharge. The difference is the hypercharge. So either you have charge 2 or minus 2 in this operator, okay? So all these dimension 5 Weinberg operator are either minus 2, plus 2, and plus 6 under the Peccei-Quinn. And if you see all the other standard model invariant operators having scalar fields that transform under the Peccei-Quinn, you have that all of them are multiples of 4. So there is no way you can match these charges, and therefore Majorana masses for neutrinos is forbidden at any order in perturbation theory. So neutrinos are Dirac, and therefore you need the right-handed neutrino. If the right-handed neutrino transform exactly the same as the rest of the fermions, then basically you form the 3-level mass term. But if you want also to explain why this Yukawa coupling is small, you can use this trick to generate a dimension 5 or dimension higher than 5 with the Peccei-Quinn chart, because this operator will transform under the Peccei-Quinn. Okay. So with that, you can have several options. One is that to use the topology of the seesaw type 1. Basically, is this. This is the dimension 5 that is here. You have the left-handed field, the right-handed neutrino, the H up, and one Peccei-Quinn field. Okay, so you be complete with this topology, and that means that you will need these fermions in here that transform as -1 and +1. I mean, they are like a vector-like fermion. Okay, so and something to notice in here is that the mass of the neutrino is proportional to the Peccei-Quinn scale. And this has some consequences. Also, something to notice in here is that you can, since all the fermions transform basically in the same way, you can have a GAT theory. I mean, you can embed this model into a GAT. It can be, SU5 is quite easy because the right-handed neutrino is something apart. But also in SO10, one of the heavy fields can play the role of the right-handed neutrino originally in the SO10, but it's not the right-handed neutrino that couples to, I mean, that is the right-handed neutrino of the light state of the neutrinos. Okay, but you can embed in SO10 as well. So since the neutrino mass is proportional to the Peccei-Quinn scale, that means that higher the Peccei-Quinn scale, higher the neutrino mass, okay? And if you embed this thing in SO10, then that means that one of these couplings is like the coupling of the top. So it's of order 1. This is free. So the mass of the neutrino is proportional to those couplings. And if those couplings, for instance, the product is 10 to -4, you have this band here. Considering the UV completion scale, the Planck mass, okay? So this mass of this guy, okay? If you lower the scale to be of the order of the SO10 breaking scale, then the suppression is less, and therefore the neutrino masses, if you take the bound coming from Catherine, this is the bound coming from Catherine. If you consider the bound coming from cosmology, that means that this will go up, and everything below that will be excluded. So if you consider lambda UV to be MGAT, the exclusion is even higher. So you can combine neutrino masses and the searches for axions to exclude this scenario. Okay. Of course, this is not the only case you have. You can also have different topologies to UV complete this dimension 5 operator. We did for type, I mean the topology of the type 2 seesaw. The constraints on these parameters are not as nice as for the type 1 topology. And of course, since you are including an extra doublet here, you have to be sure that you don't spoil this nice feature of this scenario that forbids the Majorana mass at any order in perturbation theory. So we did it, and we ensure that this happens. And you can also have kind of radiative generation of neutrino masses, a la Scottosh-Jenny. Of course, you will need some fields in here that somehow are without Bev. Otherwise, basically, for instance, if you choose, what we did is to choose one topology. If you choose this, that means that you have a doublet and a singlet under SU2. You have to ensure that those scalar fields does not pick up a Bev. Otherwise, you end up having this topology. Basically, you are cutting that diagram in here. And basically doing that, you can have this model in here with those charges. This is -5 in order to forbid the 3-level mass term. And the point is that once you break the Peccei-Quinn, you have a residual symmetry. And that residual symmetry basically tell us that these particles inside the loop are also stable, like in the B-L case, basically. So you have that this mass is coming from the loop, so you can compute it. And those fields are basically stable. So that means that you are, besides having the axions as dark matter candidate, you also have a WIMP, okay? So I don't know how much time do I have left, Giorgio?
5 minutes or so,
Okay.
but it's soft. I mean, how it will be, depends how much time do you want people to ask questions and how much time people have here.
Okay, so I will just mention that you can also have, okay, let me go fast in this. This is something apart, but we are trying to combine this also with dark matter. If you have a U1, I mean, those U1 that I mentioned before, those can be also gauged. That is why we wanted to have an anomaly-free solution, okay? Now we basically, some years ago, we observed for the first time the coherent neutrino nucleus scattering, which is a very nice phenomenon. And what happens is that you have neutrinos interacting with the nucleus as a whole. And basically for that, you need a very low energy neutrinos below 50 or 40 MeV. So either you can have reactor neutrinos or accelerator neutrinos in order to detect something. So the cross-section is basically proportional to this parameter here. And this parameter is proportional to the number of the neutrons inside the nucleus you have, okay? Basically in the nucleus, it depends, the weak charge is mostly coming from the neutron, okay? So it's a very nice phenomenon. You have that, and it is sensitive to non-standard neutrino interactions, that part. If you have non-standard neutrino interactions, then you have some contributions from the non-standard to the standard part coming from the interaction with the set. Okay, so I will just mention that you can have some model work with that, with funny charges. This is like B-L, but this is also anomaly free. And the point is that you can combine these and have also neutrino phenomenology. And the good, I mean, the thing that I want to mention is that you have pheno, blah, blah, blah. And the important thing is this, that you have constraints coming from this experiment. I mean, you also have constraints coming from LHC and Atlas above, but for very low masses of these gauge bosons, these experiments, I mean, coherent and coherent-like experiments. I mean, you have accelerator. The only observations so far are from accelerator neutrinos, and they have used 2 different nucleus. I mean, argon and I think this is using cesium iodide or something like that. But the point is that those kind of experiments, and right now there are several proposals, and actually in Brazil you have one that already ran, but they didn't see anything, CONI. But in any case, CONI, without observing, they already put some constraints. For the very low mass, those constraints coming from CONI are also competitive. And you can also include dark matter in this model. So I will conclude with that. Basically, it is possible to link dark matter with neutrinos in several ways, not only those that I mentioned here. Also with neutrino nature, if neutrinos are Dirac or Majorana, it can come from the fact of how you break B minus L, for instance. You can also have axion neutrino complementarity for searches of axions. And sevens can prove physics beyond the standard model. And this is a very hot topic right now. And for instance, you asked me something, Giorgio, before the talk about the xenon. Sevens and other kind of experiments already put some very tight constraint to some of the explanations already in the market. So I will conclude with that if there are some questions.
Thank you very much. Virtual remote applause. If people have questions, please put your name on the chat. That would be a good way to do this. And I will unmute you. Raising hands. Orlando has a question.
Yeah.
Orlando, please go ahead.
Hi, I want to ask this thing. You said about a lot about this dark matter stability. When you made these models, but you can have, for example, like one dark matter, which the one is unstable and another is stable, or you cannot do it. Or because my question maybe is more to be more clear. When you say this dark matter stability, all the dark matter particles are stable, or you can have some of them they are still unstable?
No, you can also have unstable dark matter. I mean, the only condition is that the lifetime is way above the edge of the universe, which is not really, I mean, it's not really hard to have that. To have a particle that is long-lived. For instance, we had a model on, it was for ice cube, but imagine you have a triplet of SU2 that couples two neutrinos, but with no BEV. There is something that basically forbids that to have a BEV. That is, it can be lepton number, okay? That particular particle will decay into neutrinos. So you have the triplet, and you have in the Lagrange the triplet that couples two neutrinos. If that coupling is very, very, very small, then the lifetime of this guy is huge. And it can be dark matter that decays, and you, for instance, can have signatures of the decay in ice cube if it's quite heavy. And basically, since that is basically one term de Lagrange, you can have other candidates that can be connected to that one or not. Also, you can have a dark sector that is with several particles. Some of them are unstable that decays into the dark matter one, but are so long-lived that can also play part of the dark matter nowadays. So yes, the answer is yes, I do agree with that.
Yeah, okay, thanks a lot. I didn't know this thing about the ice cube. Okay.
Carolina Carolina wrote something on chat, and she writes, in the slides, you mentioned PGD and NuFit. Could you mention this?
Yes, the PDG, I mentioned PDG not because the numbers, let me go back to that, but because the parameterization, you can use the PDG parameterization, or you can have another parameterization for the mixing, okay? Mm-hmm. So this parameterization is coming from the PDG, okay? This is one of the groups that perform global fits, that is the one from Valencia. There is another one that is the NuFit, new fit is another group. I think it was, yes. This fit is coming from another group. And there is a third group in body. So they more or less always have kind of the same numbers, but it is good to have more than one group that is doing the work. But I mean, the PDG is only to have the parameterization. Okay.
Okay.
Oh, okay, and also the CKM, this is coming from the PDG.
From the PDG. Ah, okay.
Yeah.
Okay. PGD. Okay, next, Gabriela. I'll unmute you, but you can.
Hey, thank you for the presentation. You mentioned that the stability of dark matter implied in a symmetry to be preserved. I think I did not understand this.
Well, for instance, in the standard model, you have several particles that are stable, and that is because they have some symmetry that protects them, okay? As far as we know, the proton is stable. Of course, if you have a GAD or supersymmetry with dark parity, you can have a diagram that gives you proton decay, okay? But in the standard model, baryon number is an accidental symmetry. So, and the proton is the lightest baryon in the nature, so the proton is stable. There is nothing to decay in the same way, if your dark matter is not long-lived but stable, that means that you have a symmetry that protects this particle from the decay, because this charge will be conserved. Somehow it's like that. You have the dark matter has a charge, and the small, I mean, for instance, you have in here, in this diagram, you have two particles that I tell you. Those particles are in the dark sector, okay? Both of them can be stable, but only one of them is stable because the heavier one will decay to the lighter one. For instance, if this n is the stable, I mean, is the mass of the n is smaller than the mass of the eta will decay into n and L. But n, since n has a charge, that there are no other particles that are lighter than n. With that charge, there is nothing to decay. Okay. For instance, the electron is the smallest, I mean, the lightest particle with electric charge, so it cannot decay. And the neutrino is the lightest fermion, as far as we know. So one of them at least is stable by Lorentz, okay?
I see, thank you very much.
Sorry. Next question is Mileto Graziano. He can ask it, or I can ask it in voice. He sent it to me by chat. His question is basically, can one use neutrinos in astrophysical observations to get information about dark matter? Can one use neutrino detectors to get, can one use extragalactic neutrinos to get information about dark matter? This is how I understood.
Yes, of course. I mean, well, there are many ifs, right? Neutrinos are very good for doing astronomy because they don't care about what they pass through. They can, I mean, most of them, of course, they will interact, but you will get a lot of neutrinos coming directly from the source, okay? And that is, for instance, one thing with the ice cube. Of course, I'm talking about very high energy neutrinos. So you have a dark matter candidate that is quite heavy, I mean, by heavy, I mean, more than 100 GeV. And if you see the spectrum of ice cube, of course, right now we need more data. We wrote a paper on that, actually, a decaying dark matter to explain one excess in some of the beams of ice cube. But this is, I mean, this is nothing related to where is the neutrino coming from. It's because you have some dark matter and the dark matter decays, and then you have some signals. But yes, if you have something that is very dense and you have a lot of dark matter there, and the dark matter, you can also have dark matter annihilating into neutrinos. But yes, you have to have the nature that is basically your dark matter mainly decaying or mainly annihilating into neutrinos, which is not always easy to build from the standard model. I mean, from the model building point of view. But yes, people are doing that kind of physics.
Okay, thank you very much.
Any further questions? If not, I'll interrupt the recording and thank again, thank you.